Now we are ready to begin a new chapter for our class, and this is we're going to close the chapter on the derivatives. We're going to use everything and synthesize everything to talk about antiderivatives and integrals and how they play a part in calculus as well. So let's take a look at what we know so far. Well, let us define what is an antiderivative. An antiderivative of f of x is a function, we'll call it the capital F of x, such that if you take the derivative of capital F of x, you get the original function back. So it's essentially reversing the procedure of taking the derivative. If you think about, let's say if you square something, you can take the square root to get back. It's sort of a similar idea, reversing the situation. So first let us practice finding some antiderivatives. For example, if you take 2x, try to think about which function would give you the derivative of 2x. Well, it's simple enough. It's x squared. So if you differentiate it, you'll get the 2x back. Okay, so let's take a look at and you can always check this. 3x squared will give us x cubed, of course. But if you think about it, we can also add, let's say, plus 5 or minus 1. You can also add any constant. Why is that? Well, when you take the derivative and you try to check, the derivative of x cubed is 3x squared, but the constant would be gone. So antiderivatives are usually true up to a constant. So you would see a lot of these plus a constant around because the derivative of a constant is 0. All right, so from now on, we will be adding a constant. We'll call it c. Again, it could be any constant, plus 5, minus 1, plus 21, and so on. So since every antiderivative function is true up to a constant, what we actually get is a family of functions. So instead of a single x cubed, you can get x cubed plus 1, x cubed minus 4, and so on, that can satisfy the condition of being antiderivative. Okay? And we'll explore that idea in a lot of detail. What about if we had 5x to the 4th power? Hopefully you start seeing patterns. Looks like x to the 5th plus a constant. Okay, and you can always check it. What about 1? Well, you can get x, derivative of x is 1 plus a constant again. All right, so from now on, we've chosen our functions very carefully, the little f of x, to find the antiderivative. But what about if the little f of x is x squared? Then how would we find the antiderivative? You have to think about that a little bit. The derivative of, let's say, x cubed would be 3x squared. So what's happening with that 3? Okay, well, we can actually find out there is quite a few rules for antiderivatives that are very similar with derivatives. For example, the power rule. We'll start with that basic one. If you recall, when we first learned about derivatives, that was the first one we learned also after the difference quotient. So here is what I talked about x squared already. So because there is 3x squared, something is missing. But this is what works. If f of x equals x to the any power or any exponent, then think about this. How we can take care of this constant? Well, the antiderivative is x. Notice how we increase the power by 1, or the n plus 1, divided by that power. Okay, so we're reversing the operations. Instead of taking the power down and then decreasing it by 1, we're reversing not only the operation but also the order. First, we increase the power by 1, and then we divide by that same power plus a constant. So we'll see how that works. There is that x squared. So let's see what we will get. So if you increase the power by 1, you're going to get x cubed, but then you divide by it. So it's a little bit different than the derivatives themselves, but we'll see why that works. So you get x cubed over 3. If you take the derivative of it, remember derivative of x cubed is 3x squared. And you'll still get 3 in denominator because that's a constant. So notice how the 3's will actually cancel, and you'll just get x squared. This is where that 3 goes. Remember I mentioned to you derivative of x cubed is 3x squared. So what happens to it? Well, if we divide by that power, then it actually cancels out. So yes, we increase the power by 1 and we divide by it. So you'll get a lot of fractions with antiderivatives. Okay. What about x cubed? Notice if we try this process, we can get the antiderivative x to the fourth divided by 4 plus a constant, plus c. Okay, what about 1 over x squared? Well, if you recall, just like with derivatives, so let's first write it as x to the negative 2 power. And then we can repeat the process. Remember, now we are increasing the power by 1. So the negatives would actually decrease. Well, if you think about it, you're increasing. So negative 2 plus 1, we're going to get negative 1. So it's going to be x to the negative 1 over negative 1 plus a constant. You can clean this up a little bit because you're dividing by negative 1. You can actually put this on the front. So it's negative x to the negative 1 plus a constant. And then you'll get negative 1 over x plus a constant. Okay, so you can put it in denominator as before. So yes, we always increase the exponent by 1. Now, if you think about it, before we get into integrals, this would all work, but let me pause for this. All works unless, excuse me. Sorry, I wanted to actually write something and have you guys think about it before we get into something called an integral. So this works for negative exponents, it works for radicals very same way. But what if we had x to the negative 1, if this was your little f of x? Try to think about it. What would be the antiderivative? Because if you employ the power rule, it doesn't work because negative 1 plus 1 will actually give you 0, but then you're going to be dividing by 0. What? Remember, we cannot do this. So this is undefined, but think about this. Okay, we're going to come back. But why would we want to do the antiderivative? You know, with derivatives, we calculate them to figure out the rate of change. This is what we've been doing so far, okay? Now, integral seems at first totally unrelated idea. This is where we're going to use antiderivative, but what we're actually going to be studying in the next few sections, 7 and 8 actually, that the integral actually calculates an area under the curve. And then a lot of times in business situations, for example, if you're given a rate, what if you know how fast something is increasing the cost? Let's say if you know the marginal cost, how do you find the actual cost and so on? So you actually are reversing the process, but essentially we are calculating the area under the curve when we calculate, let's say, cost given the marginal cost and so on. So historically, there was a need to solve this problem. This is why it was found this way. So I was actually trying to explain this very soon. Actually, in section 7.4 we're going to study a theorem called Fundamental Theorem of Calculus that relates antiderivatives, which is what we've been practicing with the functions, and integrals, which is the area under the curve. They were related. And this is pretty amazing. The two ideas that seem a little bit different at first were actually related. So for this course, which focuses on business applications for business calculus, we'll mostly explore the antiderivative portion. For example, if you know the rate, like marginal cost, how do you find the cost? But we do need this idea of area under the curve so you guys can get comfortable with it. So what is happening? If you have a general curve, it's very difficult to calculate the actual area unless it's a known geometrical shape like a circle, triangle, rectangle, and so on. But it's been discovered, this is actually a pretty genius idea when it was discovered. If you take a known shape, let's say a rectangle, we're going to be using rectangles a lot. You know the area of a rectangle is length times width, which is what I'm writing out. Well, in this case, the length or the height is the function at that point, so I call it f of x right at that point, times the width, we're going to call it delta x, or the change of x. We've seen this notation before, and that's the area of a rectangle. Now, as delta x goes to 0, you want those rectangles to be as small as possible. I'll show you guys a little bit later, maybe in section 7.3, how we can do that. The delta x is actually going to become dx, which is the derivative notation. And if you sum up a lot of these rectangles, in fact, infinite number of them, this is what integral represents. The integral, which looks like a fancy S, in fact, it stands for the sum. It's the sum of areas of rectangles. So for the integral, that sum actually approaches to infinity. You're trying to squeeze in as many infinitesimal rectangles as you possibly can. And I'll show you again a little bit more visually with a little applet a little bit later. So from now on, we're going to use this integral notation, this fancy S. So you got to practice writing it. Mine looks a little bit more of an S than this, the typed version, but that's okay. So we'll use the integral notation, and this is what we're going to use. An integral, notice how we have the sum. This is what the integral stands for. The length, which is f of x, times the width, which is dx. This is why you'll always see the dx under the integral. You always have to put it there because it's a width of a rectangle. And we'll see in section 7.3 why we need that. Anyway, what this equals to, once you evaluate the integral, is the antiderivative, capital F of x, plus a constant. And this is what we'll use a lot for these type of integrals. For example, an integral of x cubed times dx, this is literally times, equals to x to the 4 over 4 plus a constant. As soon as you evaluate the integral, notice how the integral sign is gone, the dx is gone because this is like the derivative part under the integral. Once you integrate it, you get the antiderivative plus a constant. This is all you get, okay? So just practice with the notation. We have different rules for the integrals, which are very similar as for the derivative. There's constant multiple again, there's sum and difference. The only time where the evaluating integral becomes difficult is if you have a product or a quotient. There is no product rule, there is no quotient rule. So a lot of times you have to either work around with different substitution techniques or like integration by parts in section 8.1, we'll see. But sometimes it's very difficult. In fact, sometimes it's impossible to evaluate certain integrals because of that. But constant multiple works the same way. A constant you can pull out and then you can integrate, or you can keep the constant just like with derivatives and integrate. And sum and difference, you can do them separately, basically one term at a time, very similarly. And we'll also be using power rule, just as before. So here's a few examples. Here is an integral of 6 times dx. Remember how we can pull out a 6? So you'll just get dx. Even though there is no 1 there, you can put a 1 there. Remember what's the antiderivative of 1 that we found earlier? That was x. And you will keep the 6. That's why it becomes 6x plus a constant. So notice when we evaluate the integral, the dx part is gone. So the 6x, you can always check. Take the derivative of 6x and you'll get the 6. So you'll get the derivative back. Okay? So you can always check that. All right. Now we'll see quite a few more. I'm just going to read through them. Let's say 2z plus 3. You can do them one at a time. 2, notice how we kept the 2. And the z becomes z squared over 2. Sometimes I write it on the top. Sometimes I keep it on the side. But this is what we get. Plus 3 becomes 3z. We're just going to practice from now on. The constant becomes the constant times the variable plus c. Again, notice how dz is gone. All right. And we can simplify. The 2 actually cancels and you'll get z squared plus 3z plus a constant. So again, once we evaluate it, you get the antiderivative portion plus a constant. Okay. Same thing we can do with 6t squared minus 8t plus 7. You'll get, notice how I kept the 6 on the top, which is okay. So you get 6t cubed over 3 minus 8t squared over 2 plus, remember constant, becomes 7t plus c. And then you can reduce it sometimes. 6 divided by 3 is 2t cubed. Minus 8 divided by 2 is 4t squared plus 7t plus c. So sometimes it reduces, sometimes it doesn't, just various. Notice how in the next example we have a product, but we cannot evaluate product. So see, you can distribute. So we'll get 5x cubed minus 40x. So if you can distribute, if you can multiply it out, make sure to do that first. So what do we get? Again, as soon as we're ready, once you simplify, notice how we keep the integral. But as soon as you're ready to simplify or actually find the antiderivative, the integral sign is gone. The dx, which is the part of the integral, the area, is gone also. So we're focusing on antiderivative. That's 5x to the 4 over 4 minus 40 x squared over 2, that's the antiderivative of x, plus a constant. So yes, x cubed becomes, notice how we increase the power by 1, x to the 4 over 4, and so on, plus a constant. Notice 5 over 4 does not cancel, but 40 over 2 becomes 20 x squared plus c. So if you practice like that. So yes, this is what I was talking about, the product and quotient rule. So you can try to multiply or divide, or occasionally we have a couple of techniques that will help us later. Let's practice a little bit with fractional exponents. They work very similar. So 10u to the 3 halves minus 14u to the 5 halves du, this is the integral, equals to, no more integral sign because we're ready with the antiderivative, because there's nothing else you can simplify. Keep the 10u. What is 3 halves plus 1? If you think about it, well, it's 3 over 2 plus 2 over 2 becomes 5 over 2. And we divide by that, minus 14u, now 5 halves plus 1, which is 5 halves plus 2 over 2, that becomes 7 over 2. And you divide by 7 over 2, plus a constant. Notice how I pulled the 10 out because you want to divide by fraction. I flipped it, make it 2 over 5. So it's 10 times 2 over 5. Notice how 10 and the 5 will cancel. That will give us 2 times 2. That would be 4. Same thing with 14 and 7 cancels, giving us 2 times 2. That would be 4 again. So we'll get 4u to the 5 halves minus 4u to the 7 halves plus a constant. So it works very similar. This may seem like a complicated problem. This next one, integral of pi cubed over y cubed minus square root of pi over square root of y dy. And sometimes on the homework, the e, which is another constant, the e that would be given, if you remember, that's 2.718 and so on. But you treat it as a constant, very similar. Remember y cubed, you can take it out of the denominator, make it y to the negative 3rd power. And same thing we did with square root of y, kept square root of pi, keep that. And it becomes y to the negative 1/2 power. That's still dy. Sometimes I put parentheses around the whole thing, sometimes I don't, but it's the same idea. So we keep the pi cubed, that's your constant. If you increase negative 3 by 1, that's negative 2 divided by negative 2 minus, keep the square root of pi. Negative 1/2 plus 1 actually becomes positive 1/2 divided by 1/2. So what do we get if we simplify? Usually if it's negative in denominator, I pull it out on the front. Keep the pi cubed on the top, and you keep the 2 in the denominator, and you can put y squared in denominator. Actually, there should be a square. I'll put a 2. Yeah. Minus, now the divided by 1/2 actually becomes a 2. You can put it in the front. 2 square root of pi y to the 1/2 plus a constant. So that's how you work this one. Okay. So remember how I mentioned that x to the negative 1 power? I think this video may become a little bit too long, but I may explain this one, and I will leave the exponential functions for the next video. So the power rule does not work, but if you rewrite x to the negative 1 as 1 over x, recall the derivative of ln of absolute value, we're going to use absolute values here because of the domain difference, is 1 over x. Remember from section 4.5, if you go back there and review it, then the antiderivative is ln of absolute value of x plus a constant. So from now on, if you ever see a variable in denominator, if it's to the single power, you get the ln there. And that's it for this video. So I'll continue for the rest of the section with exponential functions in the next video.